All right, in this video, we're going to pick up from where we left off in the last one. In our last video, we found the mean of the squared deviations in prices of the gas to be 0.00665. Well, that mean of the squared deviations is called the population variance and is denoted by, this is the lowercase Greek letter sigma being squared. So remember, population parameters use Greek letters. Our sample variables use letters we're more familiar with, like x's and the like. So just like mean has a sample mean and a population mean, variance also has a sample variance, and it's denoted s squared, which is easy to remember because we use s for sample variance here. So if it's sigma squared, that refers to the population variance. If it's s squared, that refers to the sample variance. Now, sample variance is very similar to population variance with the exception that instead of dividing by the total number of observations, so in our gas squared deviations, gas prices example, we divided by 4. With sample variance, we're going to divide by 1 less than that, which in this case would be 3. And 1 less than the number of observations is called the degrees of freedom. This is something we'll talk about in future videos as well. So degrees of freedom in this case represents 1 less than the total number of observations. So where that comes from is, remember that the sum of the deviations from the mean must always equal 0. When we calculated the deviations, we had like the 0.06, the 0.10, the negative 0.09, and the negative 0.07. Maybe I'm off by a couple negatives or what. But the sum of the deviations was always 0. And in a data set with 4 entries, the first entries can be any number we want, or the first 3 entries rather can be any number we want. Note that 4 minus 1 is 3. So the last entry must make it so that the sum of the deviations from the mean equals 0. So if we pick want 4 gas prices, the first 3 we pick can be any gas price we want, but the very last one we pick must make it where when we find the mean, it's going to have the sum of the deviations is going to be 0, and that's always going to be the case. So mathematically, it has to happen. So no matter what, when you pick that last data value, it's going to force the sum of the deviations from the mean to equal 0. So in a data set with n elements, the first n minus 1 elements can be whatever they want. So with 4 elements, like 4 gas prices, the first 3 of them can be whatever they want, but that last one is going to be forced to cause the deviation from the mean to equal 0. And it's not like you have to find what that last value is. Once you pick it, it's going to automatically force the deviation from the mean, the sum of the deviations, to equal 0. So another way to describe the difference in dividing by 4 versus dividing by 3 is that dividing by n minus 1 is actually going to do a better job at targeting the actual population variance than dividing by n will when you take a bunch of samples. And in the next video, we're going to take a look at a computer simulation of that so you can see it firsthand. But when, again, finding the... we use samples to get information about a population, and unless we have every single population value, we're going to have to use samples. So dividing by n, what we'll see is it underestimates what the population variance is. Dividing by n minus 1 is going to do a much better job and get much, much closer to the actual population variance, and that's why we divide by n minus 1. It does a better job targeting the population variance. We'll see it in a video. So because of this, we say that the sample variance is an unbiased estimator of the population variance. So the difference between the expected and actual values is essentially 0. So, but again, we'll see a computer simulation of sample variance versus population variance in the next video. So our formulas, if we put them into formula form for population, it's each data value minus the mean. Remember, population mean uses the mu value. We're going to square those deviations and add them all up, and then divide by the number of observations, which is n. With sample variance, we take each data value minus the sample mean for that sample, square it, add them all up, and divide by 1 less than n. So the problem with variance, though, in terms of using it as our primary measure of spread, are the units involved. So what happens is it actually gives us squared units. So the answer to our above example is in squared dollars. The 0.006965 is in squared dollars, which we don't normally talk about square dollars. So we need to do something to bring those back down to the same units we started with. So how do we go from squared dollars to square dollar, or from square dollars just to dollars? We take the square root of those units. So if we take the square root of the variance, that's what standard deviation is. Standard deviation is the square root of the variance. So here's our variance, just square root it no matter what. And standard deviation is going to be something we talk a lot about in this course and throughout these videos. So again, we could think of standard deviation is a measure of how much the data values deviate from the mean on average. So we saw that if we just use the deviations, the total is going to be 0, which means the average is 0. So standard deviation allows us to get a better understanding of how far away from our mean each of those values were. So how far away from our mean gas price of $3.31 each of the other gas prices were. The value of the standard deviation can be positive or 0. It can never be negative because it is a square root of a value. When we take the square root, it's not going to result in a negative. The value of the standard deviation can increase dramatically with the inclusion of one or more outliers, which again are data values that are very far away from all of the others. We'll take a look at how to find outliers in a future video. And the units of standard deviation are the same as the units of the original data values. So in other words, our gas prices, when we find the standard deviation is in dollars or is in cents, not in squared dollars or squared cents. And the sample standard deviation S is a biased estimator of the population standard deviation. So, all right, a population variance is sigma squared, sample variance is S squared, and usually values will be within 2 standard deviations of the mean. So let's take a look at using that in terms of another mean price of gas one day is $3.58 with a standard deviation of 33 cents. What interval would represent a usual price of gas? So our min usual price would be our mean minus 2 standard deviations. So $3.58 minus 2 times 33 cents is about $2.92. Then our maximum price would be our mean plus 2 standard deviations, which would be $3.58 plus 2 times 33 cents is $4.24. So our usual price of gas would be between $2.92 and $4.24. So anything outside of this interval we would consider to be unusual. Hopefully we get one that's below $2.92. That would be one that you'd want to make sure you get a lot of gas filled up in your tank. All right, so that about does it for this video. Thanks for watching. I'll see you.